Again, my name is Henry Sonten from CS Australia. I'm delegated to look after the market in Indonesia, including assisting architects and engineers to select our products. Just click this one is a bit of overview of the construction specialties, founded in 1948, privately owned by Edward Hellick, with the sales and manufacturing all over the globe, 25 countries, including Singapore, Hong Kong, China, Europe and US, and many distributors, including Indonesia. The growth of the company was fueled with the introduction of the world's first extruded aluminum louvers, which is in 1955. Our products range is CS louvers, as we all know now, the airfoil, solar motion, solar shading, and then CS data area, which is for precision cooling and control. Expansion joint covers designed for thermal, wind, and seismic requirements. This is the example that on the left-hand side is from San Francisco International Airport, where we put the floor expansion joint, and then the wall expansion joint is pretty concealed. And then also the entrance mats, which has recently installed in the data center project in near Jakarta. On the right hand side is our famous acrofin, which is many of you probably seen this one in the hospitals or aged care, and which we use that for wall protections, door protections, and also the corner guard protections. The CS explosives, which is used in many manufacturing food processing industries, which prone to explosions. As a matter of fact, the food industry is actually the highest risk for the explosion, including and also the wood manufacturing. CS cubicle curtains for the clinics and hospital applications, and also the latest one is actually the platform solution, which is seismic resistant stairs, modular awnings, and modular balconies. This is designed for the seismic to be able to move to the arrows there, so it's moved 3 directions for the seismic conditions. Right. So what the agenda for today, I'll discuss about the louvers, type of louvers, the standard related to the louvers, the performance testing, and how we can reduce the plant room size, how we can correctly specify louvers, and then boring louvers. Maybe some people probably think about it. What is the options? So we'll have a look at the next slide. What is a louvers? It's basically made from timber, steel, aluminium. It's basically to inhibit water or sand on some locations, for example in Middle East. A failure to understand, clearly express the performance requirements at the design or the procurement stage increases the risk of the products not being fit for purpose. The end users may experience unwanted water penetration and wasted energy. The type of the louvers, one of them, which is ventilation and rain defense. WDR is a wind-driven rain louvers. In this category, is essentially a grill fixed in an opening designed to let air through and keeping the waters out. No moving parts, and it is designed to perform both functions simultaneously at all times. This louver's suitability is determined by how effective it is in achieving the both functions. We'll discuss in the next details. Acoustic louvers, which is the purpose of this one, is to reduce the noise transferring from one side to the other side. It does has a small free area and then high in pressure drop, but as we know, the function is mostly for the noise reduction. The sand trap on the left-hand side is commonly used in Middle East projects to resist intrusive sand, and usually with the design as a vertical orientation. On the right-hand side is the screening louvers. We have called Smart Click, which is the purpose is for fusion barrier, which is fast and then easy to install. Explofen, which is mentioned before, one of our products, is a first resettable explosion that can be field tested. On the right hand side here is the blast resistant louvers for government buildings, embassies, for example, hospitals, data centers, power plants, which are particularly vulnerable to the explosive events or explosive threats. And CS has developed 6 blast resistant models designed to withstand the blast up to 83 kPa, kilopascal, and then this meet the government requirements. The sun shading, 1956, CS introduced sun controls to the architects community for the aesthetic, reducing the sun glare design for energy efficiency, energy conservation inside the buildings is of utmost importance. Next slide is about our louver blade styles. In the US, they might be called as they call J or K blade. In Australia, we call it as Z blade louvers. They are conventional louvers. The blades actually do not provide a good rain defense. The next one is our wind-driven blade louvers, which is shaped aerodynamically. This is to provide a separation between air and water. So this process is called the tangential separations. There are actually the 3 testing standards in the world. Basically, it is the standard of Australia, the Australian standard, New Zealand standard 4740 2000, and then also the AMCA, the American standards, and then the British standard or European standards. 13030 2001. So the purpose of this is to standardize the requirements and then performance criteria for manufacturers and users, including architects and mechanical engineers. The standards, they also mention about the testing rigs. This is something that we have in construction specialties, is the in-house testing rig in our US facility. The AMCA Australian standard and New Zealand standard, and then the European standard covered the same protocols in the pressure drop and then the wind-driven rain. If you see on the left-hand side, bottom left, there's the louvers that's under the test. What happened is with the wind and then also the rains on the left-hand side, it's basically simulated rain. And also on the right-hand side is the fan, which is acting as the air intake velocity to apply to the louvers. Performance criteria of the louvers is simply make it into 2. One is the air performance and then the water ingress performance. The air performance is measured in pressure drop or Pascal. Pressure drop is the difference in pressure between 2 points of the flow system, referred as the air performance. The resistance to the flow, it can be caused by the turbulence or frictions through a louvers. So it could be the shape of the louvers is not providing the airflow effectively. What happened to this one is this will affecting the measurement efficiency and energy usage of a mechanical device. So if we are going to consider green buildings, so pressure drop is something that important to consider. In fact, for the Australia, there is a national construction code. They put the pressure drop into the energy efficiency as the requirements. Free area, I think most of us seen this one, free area, 50% free area, 60% free area. Whether it's enough, we'll discuss about. So free area calculations is simply the calculations of the minimum opening areas between blades and then blades and frames, and then also between blades to the jamb. So that will be given the size or area, and then also then divided by the size of the louvers that give you the free area. It can be calculated for any single shape of the louvers through the cross-section of the louvers. Whether it's 50% free area, really 50% free area. So actually the percent free area is not an indicator of overall performance louvers. It's only indication for louvers that may be suited to handle the larger volume of air. Therefore, free area should never be used in determining the louver's air performance. Another reasons why you don't go by 50% free area is because the free area changing by the size of the louvers, as you can see, or you can be calculated through the formulas before. When you change the size of the louvers, the percent of the free area is also changed. So the smaller it is, the free area is also dropped, and then will change during the sizes when the size increase. Let's do a case study. So it's basically we try to compare between 3 different models of louvers. The left one is the conventional louvers with the 50.4% free area based on that calculations. The middle one is the wind-driven rain louvers with only 45.8% free area. And also the right-hand side, wind-driven louvers again with the 50% free area. The right-hand side is a deeper size of the panels. So it's 125 millimeters deep, and then the right-hand side is 175 millimeters deep. Let's do the comparisons through the testing results, which reflected in calculations that our engineers has prepared. We'll get the results in the next slide. So this airflow calculator is already made available in our website. So anyone can just jump into our website and then put the informations in. So it's basically entering the width, the height, wind pressures, and then just keep going with the prompt. It will give you the indication of what the size of free area based on this using that type of louvers. And then also it will give you the pressure drop when you're providing the information of the flow rates. I guess before to see the result is the intention here is to have the lowest pressure drop as possible for energy efficiency, because the lowest the pressure drop means the better is the energy efficiency. Or with the same pressure drops, how much air can deliver in liter per second. So the liter per second is actually the key deliverable for the mechanical engineers. If you see this, surprisingly, that the 125 millimeters wind-driven rain louvers with the smaller free area providing higher liter per second of flow into the other side. So, and then also with the 175 millimeters deep of the wind-driven rain louvers with the 50% free area, it's actually have almost 20% less air than to the other designs. The next one is about the rain defense. So usual response designs and construct builders saying we never needed a certified performance louvers. So why now? So I think if you are told that you never had a problem, so just be skeptical about it. This is the next one that we based on the information from AMCA laboratory, basically summarize the comparative performance of conventional louvers versus the wind-driven louvers. The test is based on standard with the 13 millimeters per second wind velocity and then 75 millimeters per hour rainfall rate. It's basically 29 miles per hour and then 3 inches per hour of rainfall. We're comparing between the standard louvers, the drainable louvers, the single stage louvers, the single stage drainable louvers, and then also the wind-driven louvers. On the right-hand side, with the standard fixed louvers, the numbers we get is 29 liters, so it's almost 30 liters. And then for the drainable louvers, it actually doesn't help a lot, so it's still above the 25 liters. In comparison, the wind-driven louvers is actually only close to 2.5 liters. Consider this, that's basically, this is the 29 liters is per hours per square meters of the size of the louvers. So if you have 3 buckets, 2.5 buckets there, so on each buckets is 12 liters, you're going to have 2.5 buckets every hours in every meter square of louvers. Water penetration classes in standard testing. These tabulations showing the effectiveness of the louvers based on the 3 standard testings. It's actually the same between AMCA and then also the Europeans and then the Australian and New Zealand standards. So they use the same numbers, exactly the same maximum allowable penetrations of simulated rain. If you see the class A, it's basically you can only allow 0.75 liters per hour per square meters. And then class D is more than that. So that means with the louvers, that conventional louvers, so it's going to be mainly class D. How we can reduce the plant room area. Consider you design a plant room and use the conventional Z louvers. Due to number of wind-driven rain, and in order to protect the equipment, you need to edit the plenum. You may get saving of the louvers, but the cost of the plenum and additional area required would probably be more expensive in the long run. So the real estate value, which is you can saving it it's going to be gone. So with the smart design Louvre, so if we're going to use this one, so it's going to be slightly more expensive, but you're basically optimizing the plant room area. And then again with the water entry prevents and rain defense, will any of the followings will occur: damage to the electrical equipments, damage to the HVAC equipments as well, potentially damage to the interior of the buildings, finishes and structures. Mold can grow. It could be any slippery fall hazard and many other situations that may cause from water infiltration to the buildings. And if you see on the right hand side here, I don't think that's the plastic covers. It's part of the design as well. Now I'm just going to show you what with the tests that done on the Louvres, single stage Louvres. It's one of our Louvres that we use for the open deck plant rooms, and then we're going to see this video from the front view. The number of waters is basically also coming in from the inside. We're going to see what's happened to the inside of that. That's going to show that the Louvres has the waters coming into the buildings and potentially can create, they could be a hazard for slippery and also the damage of the internal side of the buildings. In comparison, we have RSH 5700, which is we use quite a lot for the wind-driven rain louvers. We're going to do the similar test, but at this time we're going to increase wind at the 22.4 and then 200 millimeters per hour rain. This test is actually above the Australian and New Zealand standard, and also above the European standard, but this is part of the American ANCA standards. The waters is actually channeling to the side and then drain down and then flow up outside of the buildings from behind. So this is what we're going to see. It's very small numbers of waters coming in, almost whereas like what we have, it's going to be, this is part of the class A of the Louvres. How we can correctly specify a Louvres? I guess 50% free area probably no longer relevant. It is still used, but it's not finalizing, not giving the final result of what you're going to expect for the building. So in the minimum specification, you should allow for what is air performance. For example, the air performance needs to be 25 Pascal or less. And then also the wind-driven performance needs to be a class A. This is only can be attained from tests. The next one is Louvres is boring. I hope there's a number of architects here. So ruins the looks of the building. So what we can do, so what CS listen and then try to accommodate with the demands from the architects. Flexible design elements. Anyone maybe consider vertical blades. For example, this is one of vertical louvers at the Madison Square Gardens. And we actually use quite a lot currently designed for some of the projects in Australia with the curve as well, very flexible in the curving. The next one is the horizontal but curve. This usually it can be achieved up to 1 meter's radius depending on the blade profile selected. This is to create the remarkable facade on the roughless key complex. The architect specified the CS custom continuous line storm resistant louver. So this is a custom made. To achieve the desired result, CS developed a special seal extension to create a textured fenestration. Another one is the same one, which is the board line system, which is you can incorporate the LED lights, for example, for this for the louvers. This is what we introduced quite recently. It's basically let me just come back to this one. It's a PL5700, which is used. It has a perforation in front of the louvers, so it's try to eliminate the line of the louvers and then replacing it with the perforated. And then this actually tested to the European standards, EN 13030. Before I conclude the presentation, I'm probably just going to share a bit of video, if I may.
To allow airflow in and out of the building, they often have to provide protection from rain ingress. Louvers can also be used to provide aesthetic and economic screening for unsightly equipment or building facades. The CS Louvres range meets all these needs, delivering both the performance your building requires and the look you desire. If you're looking for full weather protection, our rain defence models are designed to deliver industry-leading performance and spatial efficiency. They offer up to 100% protection against water ingress, while still allowing good airflow. Suitable for projects where economy is a consideration, our ventilation louvers allow maximum airflow for applications where occasional water entry will not cause significant problems. Screening louvers will hide plant or other equipment while still allowing essential airflow for plant machinery. They're typically used in areas where potential rain ingress is not a problem. Where sound attenuation is required, our acoustic louvers can be used as standalone screens, integrated into building facades or hidden behind any of our louver range. With CS architectural louvers, you can bring colour, drama and excitement to your facade. Whether you're considering our standard range or would like to create something cutting edge with our new CS Bold line or CS Perform options, we can work with you to help you realise your vision. To meet the performance criteria of your project, CS Weather louvers have been rigorously tested by independent third parties. In addition, any of our standard or bespoke louver designs can be tested in our exclusive test chamber under real-world conditions. Whatever your building's ventilation, screening or weather protection needs, CS has a louver system to meet your requirements. Download our brochure to learn more, then get in touch and tell us about your project.
So I think that's conclude my presentations. Just for the information, if you have any questions outside here, just feel free to give me a call. And we also do a full CPD training for the products. Thank you.
So, Pak Henry, before we move on, I'm just wondering on the images or the photos that you shared with us earlier, a part of your presentation. So basically, can the Louvre be integrated into the curtain wall system?
Yes, it can be designed like that. So we can, in some projects, we actually custom design the connections between our jamb, our head and sill, in order to connect it compatible to the curtain wall system.
Your testing facility, or is the testing suitable for cyclonic region as well?
This MCA standard actually has the next level of the cyclonic testing. So they call it the MCA 550. So it's actually tested to the very high wind load. So it's up to, I think top of my head, it's 177 kilometers per hour, high velocity wind-driven rain, and then to pass, the louvers must be able to block 99% of the waters. And CS has the 6 type of louvers that comply to these cyclonic conditions.
So yeah, obviously Louvre can always be part of the beautiful dressing of a building, right? I mean, like, it's not only functional, but it also can be a look that architects or designer consider, just like the KPF One Rafalski building. Is that what you were showing? I think it's very beautiful. It doesn't shown as like a mechanical Louvre or like more. It's actually gel really nice with the whole thing. I'm familiar with that building. How can the additional perforated screen in front of louvers not reducing the airflow?
It is not reducing the airflow. We actually test that one. So we have, so we're maintaining the gap between the louvers and the perforations. So we designed providing the gap between the perforated louvers, the perforated metals to the louvers. So that's by that having that gaps is actually maintaining the airflow, and they are tested to the European standard.
Oh, okay, because of that air gap, basically. That's how you maintain the air, maintaining the air circulation. Thank you, Pak Henry. Thank you.
You're welcome, Putri.